Yesterday.
Awesome. Awesome. Okay, now. We have been doing a lot of face stuff lately. We're going to continue to do face stuff because I can promise you that this paper is only going to be, there's going to be at least 2 sessions long. And the main reason is because the last part of this paper, we don't understand it all. We need another week for that. So if we get to the last part of the paper before the hour is up, we're just going to stop. I'm not even going to try to bullshit my way through this thing. 5 3D shape. What's the name of this paper again? I need that. You can't have that. Shape regression. Real time. All right. So first off, we're going to start with some screen sharing here. Let me do a little screen sharing. I'm going to share with YouTube, and then also share with this. So I'm actually going to start out with a thing called Face Warehouse. So first of all, this is all work done by Chen Cao, this guy down here. And like I said, in 2012, he started a series of papers. I think there's a 12, a 13. There's definitely there's a 14. Today's paper is a 14. There's a 15. Today's a 13. 13. And then there's a 14 and a 15.
16. So.
And yeah, I think he's got a whole series of papers on this stuff. And this thing that we're going to look at first is one of the key things. So this is not the paper we're talking about. This is one of the foundations of stuff.
Okay. By the way, I think he's at Snapchat.
He's at Snapchat now, right? Yeah, he's around here. I have never met him, or at least I don't think I have. But his work is stunning. So this thing is something that's the foundation of this paper. So what he did is he had, and there's no narration on this, but I've taken a look at this paper. So he had 150 subjects, found and asked those subjects to all make similar expressions. He had a table of expressions that he wanted to do, and he, by the way, he's doing this in front of a Connect video camera. So let's go through this a little bit. What happened there? No, I broke YouTube. Sorry, let's do it back. I didn't break YouTube, I just used it improperly. So we have a whole bunch of things, and this is really a face warehouse kind of thing. You're going to start to see exactly what he's put together. So 150 identities, see that thing down there? And then 20 different expressions. And this is the stuff that he captured, right? And the cool thing is, he did it while everybody was facing a Connect. So they got 3D representation, a relatively decent 3D representation. Now, one of the first things they did is they also used various pieces of technology to take that Connect stuff and turn it actually into models that can, animation, blendshape kind of things. And they put together this thing called Face Warehouse. And we're actually going to go through some of the construction. I guess I didn't have to go as slow as that. So you have RGB input, Connect Fusion, smooth depth map. All right, we clean this up with the 20 different expressions. Then there's this thing, facial feature points, very important. There is a paper that we already covered in Chalk Talk back in 2015 called, oops, and I'm gonna turn this on here, sorry. We get to the same place here with this. There's a paper that we already talked about in 2015 called Face Alignment by Explicit Shape Regression. And this paper, Face Alignment by Explicit Shape Regression, is a brilliant piece of work. We went over it over 2 Chalk Talks in 2015, and it is the foundation for the current paper for today, and it's also a big part of Face Warehouse. And what it does is it automatically figures out where a face is in the scene, and so that you can kind of see in this image here that this guy has dots on his face, right? You can see that there's a whole bunch of dots on this guy's face, and that's found automatically by Face Warehouse. I mean, not the face alignment by Explicit Shape Regression. Now, this is a wonderful paper, but what it's doing is finding the 2D locations of those features on that person's face. And that's important because that's what Cao is bringing to the current paper, is that he isn't just finding those 2D features, he's also figuring out how the face is in those things. So he's finding 3D data, not only the 3D location of those features, but also the pose of the face at that point. And you guys can come on in, there's plenty of, you know, there are no cameras active right now, so you can walk around, you could dance, you can do anything. All right, so now, that then gets turned into expression models. And the expression models are a facts-based rig, right? So you correct me, because Rishabh's been working on this stuff as well. And then once we have that, we've got the generic blend shapes that we're going to be using to modify the expression models so that we actually have individually coded blend shapes for each one of the 150 people. And at the end of that, you have this cool-ass database. So there you go, individually coded specific blend shapes for the people. And at the end of it all, you have this really neat database that's a three-dimensional thing. You've got vertices, identity, and expressions all lined out there. So you have this, this is a full-on tensor. And by the way, there's some stuff down at the bottom here that says N mode SVD, blah, blah, blah. That becomes important and complex, but and we'll talk a little bit about that today.
Good question, though. Are they doing any corrections to the face shapes?
Yes.
To make them pure fact shapes from the actual actor expressions?
Yes, they're running on the example-based facial routine stuff. So taking, using the expressions that were actor-specific that came from the Kinect capture to then modify the generic face blend shapes to make the facts shapes look more actor-specific.
Yep. And also there was some cleanup work, the automatic feature detection kind of thing. They call this very much a semi-automatic kind of thing. So they've spent some time crafting this thing so that the features they found were placed by hand to make sure that they were placed on the right spots.
So it was an automatic feature tracking.
The automatic feature tracking was used initially, but then they went through and corrected every single one of them to make sure it's a reasonable kind of thing. And then the rest of this video is basically, okay, well, now that you have this, there's some pretty cool stuff that you can do with this. You can, you know, this face replacement, you can do all sorts of neat stuff. I'm going to fast forward past this. One of the neat things here, this is pretty cool, right? We get this guy's image, and there's Cal up there. You're sitting in front of the Kinect. You get the 3D avatar, and then you can use that to apply. He's basically animating that 2D image. That's pretty cool. And you can tell why Cal is at Snapchat. and hence there's there. And even after this, there's a very cool one. There's a good old Beethoven there. At least I think that's Beethoven. And boom! All right, respect. This is pretty cool. And this is just the beginning. This was 2012 when he was doing this. So he wants to be able to take this and push it farther and further. All right. So now we're going to stop this. I encourage you guys, just it's a first Google, just Face Warehouse on YouTube, and that's the first thing that pops up. But then this is today's paper, and I included the link there, but I'm just going to run today's paper to make sure that everybody is up to speed on this. This does have sound.
Our system only needs an ordinary web camera and can accurately estimate the 3D positions of a set of facial landmarks. From these 3D landmarks, we can compute the rigid transformation of the head and the non-rigid facial expressions, which can then be transferred to a digital avatar to drive its facial animation. As you can see, our system can well handle non-frontal faces, fast motions, and exaggerated expressions. These facial motions can of course be transferred to other avatars.
Now, one of the key things, I'm going to pause this here just for a moment. You'll notice in the picture of cow on the monitor, there are some dots on this thing. And one of the things that comes up in the paper is that the dots are different than in the original face alignment by explicit shape regression. And we'll talk about why those dots are where they are. It sort of looks like a Batman mask or something up there. But the key thing is that they are three-dimensional locations, where in the original paper, where it just locates those things, those are 2D points. These are actual 3D points, and that's part of the magic of this paper, is how that goes there. And when they're doing the transfer, they're actually solving for the blend shape parameters for his face that produces this thing, and then transferring it onto different characters is actually the easiest part of this whole thing. They're just copying the blend shapes. He's produced a fax rig for this character that matches the fax shapes for his thing, and then it's just moving the blend shape weights over across the thing. So there's not much fanciness going on there.
Is this using a depth sensor as well?
No, this is all one camera, dude. That's the amazing thing, right? This is just one web camera. And a little bit farther on, you can see that it's pretty sensitive.
Our system may generate incorrect shapes under larger occlusions.
So yeah.
Even in this situation, once the occluder moves away, we can recover the shape correctly.
Works with glasses. Even as somebody shining a light on him, it's pretty robust in terms of changing things. But at the end of the paper, he does acknowledge the fact that it could be a little...
The system can also handle lighting changes to a certain extent.
Here we go.
Here we use a lamp to change the lighting. It can be seen that the system works very well.
But he does bring this up in the conclusion part of the paper, that this
now
is
we briefly describe our system pipeline. In a one-time pre-processing step, we ask the user to act out a set of standard facial expressions and capture the images. For each captured image, a set of 2D landmark points corresponding to certain face features are semi-automatically located. Given these labeled images, and with the help of a 3D facial expression database, we compute a 3D expression blend shape model for the user and construct the training data of facial images in 3D shapes. From these images and shapes, we train a user-specific regressor that maps 2D image appearance to 3D shape. At runtime, this 3D shape regressor is used in calculating the 3D positions of facial landmarks from a 2D video stream. The head's rigid transformation and facial expression parameters are calculated from the 3D landmark positions. They are then transferred to a digital avatar to generate the corresponding animation. Here we compare the feature tracking results from a 2D regression approach, an optical flow-based approach, and our 3D regression algorithm. Our algorithm achieves much better results. For the 2D regression approach, with the faces oriented away from the front, the computed shapes may deviate significantly from the ground truth. And for the optical flow-based approach, it may accumulate errors temporally and produce drifting artifacts. To further evaluate the accuracy of our 3D regression algorithm, we compare our results to ground truth depth maps acquired from a Kinect depth camera. Using only the RGB data, our algorithm can generate 3D shapes that match the ground truth depth maps very well. Now we show more results under different lighting environments.
And now we're going to stop because we want to get into some of the details. But this gave you a good foundation of how this thing behaves. We're going to go into try to figure out how it actually does that stuff.
Tracking looks really stable.
And we'll find out how that happens too, because there's some cool stuff. So let me just quickly switch over to the right cameras here. Put this here, boop. So you can see everything, not too far away, and we're good. Okay.
You're gonna write now, right?
Oh yeah, totally. Yeah. All right, so what do we want to start with? Well, let's actually start with the paper, and then when we get to various bits and pieces, like the face warehouse, we're going to branch off and talk a little bit about that. But now that we've seen that, first talk about the steps of the paper. So first, step one, create, or well, let's say create, get images. So this is a little, like I said in the Chalk Talk announcement, this is not the paper we want to do. There is a follow-on paper in 2015 where this step doesn't have to happen. At the very beginning of this paper, what the author is asking the person to be tracked do is sit in front of a camera and take some images. I think there's around 20 different images. Well, we'll talk about it exactly. But they're going to take certain images of the person in various poses, various expressions, and various orientations. The follow-on paper, 2 years later, he was able to get rid of this step. But this is an important step for us right now because it also explains kind of how this whole thing works. So, step one, capture setup of images. And let me make sure I get this right. The first, okay. So we first capture a predefined sequence of setup images consisting of the user's face under different facial configurations. So first of this is due to rigid motion. So there's 15 head poses in a neutral expression. And again, like I said, he figured out a way to get rid of this, but what he's doing here is kind of cool anyways. And this is, there's yaw, pitch, and roll. The user is in a neutral expression, and we go from negative 90 degrees yaw to positive 90 degrees yaw, and negative 30 degrees pitch to 30 degrees pitch, and then roll, which is negative 30 to 30 as well. So, obviously, pitch or yaw would be like this. You take it and you're going all the way from a profile position all the way through there, and you're doing it in 15-degree increments. No, this is in 30-degree increments. This is in 15-degree increments. So this goes 30, 15, 0, positive 30, that way. This way is roll. Pitch is this. So we're doing all that, and we do this, and we get 15 different poses out of that.
So you're telling your subject to do this?
Yes.
Like, okay, we want 60, negative 15, and 30. And
This won't work for movies. This won't work for anything, actually. This is a bit of a scientific kind of thing, but that's the way it's going. Remember what he did when he did Face Warehouse. He got 150 people, I don't know if you paid them or not, to do similar kinds of things. It wasn't as extensive as this because they were going to do some stuff, but he still got 150 people to do this kind of stuff. All right, now we're not done. The second class is non-rigid motion. So here we're going to do 15 different expressions. And luckily, we don't have to do the expressions in these head poses. We're doing those separately. Oh wait, I take that back. Expressions at 3 different yaws. Negative 30, 0, and 30. So I'm going to do a set of 15 expressions in this pose, and that pose, right? So there's some definitely work. And these are things like, okay, so what we're going to do is expressions that vary wildly among different people are used. Specifically, mouth stretch, smile, brow raise, disgust, squeeze left eye, squeeze right eye, anger, jaw left, jaw right, grin, chin raise, lip pucker, lip funnel, cheek blowing, and eyes closed. There you go. I'm not going to write those down. You can learn the data. So in total, this all adds up to 60, according to him, images for each user. All that 15 times, is that right? Yeah, that sounds about right. Yeah, 15 plus 3 times 15, 60. Perfect. All right, that was easy. So now we have 60 images for anyone who wants to use this system. Remember, this is the system in 2013. So we get some exciting images, and that's it, right? So 60 images come out of this. Step 2 is to landmark the labels, or label the landmarks. It's the landmarks. And what are landmarks? The landmarks are going to be things like the corners of the eyes, the nose, the brow, and all sorts of stuff. They actually have 75 different landmarks. Okay, there you go. All right, and they basically say any alignment that we use could be done, but they use the face alignment by explicit shape regression. I'm going to write this down just so it's recorded. But we're probably going to cover a chunk of this paper next week because explicit, it forms the foundation of the second part of this paper, shape regression. And the cool thing about this is you do not have to write this. There is a program out there called a library out there called dlib. And dlib has a facial landmark discovering program that is based on this paper. So dlib has actually got an implementation of this paper. And you don't even have to know how it works. Now what this does, after all this does, is it comes up with 75 different landmarks on the face in each one of these expressions, and it tells you the 2D location of this. So we get 2D location only. We haven't even talked about 3D, remember? 2D images going into 3D things, or 2D locations. Again, like the face warehouse, this is user edited. This thing, as you can see from the little demo that we showed, is not always correct. And so there are times that you want to help it out, and and remember, this is the setup. This is how we're setting this thing up just to be used. So we're going through and taking all 60 images, finding the 75 different 2D landmarks on the face, and making sure they're correct. Once you do this, you never have to do this again for that user. Unless there's a lot of weight gain or something like that. I don't know. We'll see. Okay. Cool. All right. Now, next part. Step 3. This is the hard part, and this is what we're going to talk about mostly today. 3D shape regression. So the question, oh good heavens, what did all these, have you guys been breathing or something?
Why, that's a trouble.
Yeah. So now what we want to do, the ultimate goal of this, before we get to anything where we're sitting the guy or the gal in front of a web camera where we're doing automatic tracking, is we want to build a 3D model of our person, our subject, who's going to be sitting in front of the web camera. And so this step here is to say, all right, once we have these facial images, can we actually build user-specific blend shapes? And the camera location for each one of these images. So think about what's happening here. There's a bunch of unknowns. We've got somebody sitting in front of a computer here with a web camera on top of the computer. Here's our person. Nose, smiling, ears, hair. And there's all sorts of stuff going on. First of all, this person looks like that person. There's a specific identity to this person. So we want to be able to build out some sort of set of blend shapes that represent how that person looks. There's also, once you get past just the basic look of the person, how this person's face is configured. What kind of expression they're making. How are they, right now, they're that little drawing, they're smiling. And then there's also the relationship between the person and the camera. I can be moving closer and farther away from my web camera. I can be doing all those poses that they had me do to create those images. And that has to be discovered as well for this to work. We need to know how I'm facing in front of the camera. So there's identity, there's expression, and then there's pose. And all of those things are completely unknown at this point. The only thing we do know is that if I look at an image of myself on this and the thing here, I see myself here, there are certain features on my face that I know where they are. I have the corners of my mouth, maybe some chin, my eyebrows, all those kind of things are actually located in terms of 2D. That's it. So, how the hell do we actually figure out all this stuff? All right. Well, that's the first part of this paper. And the paper is divided into 2 sections. First part is doing what we're going to be talking about right now, is figuring out the blend shape model. And then once you have that, then the second part is actually running or figuring out how to train the system so that you can figure out this pose very rapidly in real time during a session. All right. So I'm just checking here to make sure I know what I'm doing. Oh, okay. One thing that I did want to talk about. 3D face mesh that matches them. As the mesh vertices corresponding to the face's contour may continually change in the video stream, for computation efficiency, we replace the 15 contour landmarks with 15 internal landmarks whose 2D position in the image are computed by projecting a set of predefined vertices onto the fitted mesh into the image. Oh, well, what? Well, the reason that this is even mentioned is that if I've got a face and I use this paper, so here's my face. Actually, I can draw a little bit more detail. Here's my brow, here's a little nose, here's my This paper, when it actually detects features, has a set of features that it spits out, blank, 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 like corners of the eyes, corners of the nose, the tip of the nose, some things along the eyebrow and stuff. But more importantly, it has 15 points that it finds along the sort of contour of the face, which are very cool, actually. You know, that's when this paper works, it's really neat to see that thing basically following your chin line. But this paper, the paper we're currently working on, says, hold on, these things change all the time. As you're moving along, these 2D points that it's finding are actually sliding all around the face. As they really are finding that chin line, which is very view dependent. So they say, screw that. We're going to change that around. And what we're going to do is use this mask that you see. There's this sort of facial mask that looks like that. Something like that. And that is their replacement for these guys. They're projecting this 2D, these 2D, or they have their standard mask that they're going to be projecting into 2D on this thing to sort of replace the chin line. And you can see that in the results, it actually works really well. I think this is a sort of clever idea. They are not getting the jaw motion, but I think for their purposes, that's okay. Rashab, I want you to yell at me if I'm saying anything wrong. Rashab has actually been working on some of this stuff. Okay. So now, 2D, I'm just going through to make sure that I'm not missing anything. All right, we'll talk about regression later. All right, so here we go. Are you ready? How do we figure out the face? They're going to build this thing, this regressor. First of all, what's a regressor? I want to make sure everybody's up on board here. Especially in machine learning, there are two things. There are two words that come up. There's classification and regression. And this regressor applied, well, obviously regression. And with machine learning, it basically means that if I have a picture of a cat, and I throw it through this sort of black box of machine learning, and it spits out a cat. It has classified this. And in fact, a lot of classification is like 0 or 1. Is this an image of a cat? 1 or 0 pops out. It's classified this into a 1 or 0 kind of possibility. On the other hand, if I have something that represents continuous data or something, a lot of good example is stock prices. If I have stock prices that are going in here, I don't want something to tell me whether or not that's a stock price. I want to tell me what the next stock price is. And so this is a floating point result. And this is a prediction of whatever this thing is. And that's what regression is. And so when we hear this, we're building basically a black box that takes 2D images and landmarks, puts it into this thing that spits out 3D locations of our features or blend shape information. And that's what this regressor is doing. It's transforming this one set of data into another representation that's a continuous thing. It's not a classification. It knows that we're looking at a person. We want to know what person. Just a quick little side note there. All right. We generate user-specific blend shapes from a user's setup images with the help of Face Warehouse, a 3D facial expression database. Now we're going to talk about how it's used before we talk about how they actually built it. We may wait hold off on talking about how they actually build it for another talk. So what we have in this thing, let's draw that thing that we saw on the video. We have a tensor. And we're going to have to talk a little bit about this before, but there are a couple of different axes of this. If you think about one column of this tensor, that one column represents 111 or 11,000 mesh vertices. So for every face, we have 11,000 mesh vertices. And along one of the axes, we have identity. And along the other axes, let's do it this way, we have expression. So if I knew that Bob had gone through this experience and had his face put in Face Warehouse, and I wanted to know what Bob looking like angry would be, I would go to the axis, or the axis that corresponds with Bob over here, which would be this guy right there, and I could get a slice of Bob. And this little slice of Bob is Bob in all sorts of expressions. And if I went to the angry axis over here, or whatever the hell it is, I could get Bob's actual expression. Now all of a sudden you can sort of see what kind of cool power that you have with this Face Warehouse kind of thing, right? We have axes of identity, and if I wanted to slide between Bob's different expressions, I just travel along this direction and I get a whole bunch of expressions that look like Bob in different expressions. But if I wanted to slide along this direction, I could go through a whole bunch of different people looking angry. And all of a sudden you can start saying, hey, this is kind of cool. I can start blending around. I have this big database, and it's a huge database, right? Now, one of the things that they did in Face Warehouse, and we're going to do a little side note, is they took Connect, and then they smoothed the crap out of it, and then they converted it into nice shapes, blend shapes and stuff. Well, I mean, meshes. But there's something interesting that they do along the way. They do a bit of a thing. Initially, this starts out where this thing is referred to as T. It's the expression tensor that represents all this matrix stuff. But they do something that was a little surprising to me in that they're actually asking a person to make an angry expression. that doesn't really make sure that everybody is in the same angry expression. They want to make sure that this thing is using the principal components of that angry expression and the principal components of identity. So they take this T, and this is why it's going to be later in another chalk talk, is they do a little magic where they run a SVN on it. Or SVD, not SVN. SVN is a check-in thing. SVN on T to extract the principal components. Now, Rashab and I were looking at each other this morning and going, can you run SVDs on three-dimensional matrices? It turns out you can. And you've got to read this Wikipedia paper. It's called Higher Order Singular Value Decomposition. And it's got different names because it's so cool. It's got Tucker decomposition and M-mode SVD and multilinear SVD and higher order SVD. It's got 4 different names because it's that cool. But think about what an SVD does. An SVD is basically a way of looking at, if you look at an SVD of a normal matrix, if this is just a matrix of data, an SVD is a way of thinking in terms of, I'm going to take that data, I'm going to rotate it a couple of ways. I'm going to break it apart into 3 different matrices, where each one of those matrices are sort of orthogonal to each other. And it's a way of extracting the good bits of the data inside here. You could have a jumble of data in this thing, but after you run an SVD from it, you basically get the principal components. What does this thing do to your data? We can do the same thing with this. You can run an SVD on this, and it will return, if people are up to speed with an SVD, on a typical matrix, it creates a U, an S, and an SB transpose matrices. It breaks a normal matrix into 3 different things. A multimodal SVD will break it into, let me get my math correct here so I'm not lying to you, a whole bunch of sums, where if A is a tensor, it's equal to the sum of the sum of the sum, however many dimensions that you might have, of S sub, and then the subscripts get crazy on this thing, and U, and U, and U. There's all sorts of as many U's as you want in here. So this thing becomes this for a multimodal kind of thing. I'm waving my hands a lot here.
But the U's are different. No,
the U's are orthogonal to each other along the, there's 2 different orthogonalities. There's the dimension that you're on, and also the user, so the U's are aligned to the different axes of your data. And so yeah, the U's, one U is this way, the other U is that way, and the other U is, well, whatever. You can have as many dimensions as you want in these tensors.
So we're taking the principal components over expression and over identity and putting it all into the same thing.
Absolutely. And the cool thing is, and the reason we did this is because the next equation that they came up with, and I'm going to write this down, a face is equal to CR, and CR is the SVD. CR is equal to the SVD of T, where they've done some compression on it. One of the cool things with the SVDs is that you get the middle matrix USV3. That's the singular values of this. And singular value returns, this is basically a diagonal matrix that it's usually just a vector. And the higher singular values mean that the more important parts of the matrix. And the lower singular values will get very close to 0. And it turns out that if you just want to compress this matrix, you can just throw those suckers away. And they do. They say there are some expressions in here that don't really matter. We're trying to pull out the core expressions from the faces that we capture. So CR is what they refer to as the core tensor. And then, this is the cool notation that I did not know until yesterday. WDIE.
Can you do the principal components of the tensor and the expression combined, or is it just exclusive?
Can I, what?
Can you go this way, the principal components of going this way?
I don't know the answer to that. I was going to make a guess, and then I thought, nah, I'm going to slow down on that. So, after you do all this stuff, there is a weighting vector, and this is just a vector, and this is sort of a weird cross-producty kind of thing, which tells you which dimension you're cross-producting this tensor thing. Because remember, this is not a 2x2 or a two-dimensional matrix. So you have to specify which axis you're working on. And so this, WID, is the weights. Let's say, where am I inside this expression space? I mean, the identity space. And this is where I am in the expression space. This is the cool thing, right? Face Warehouse has 150 people. Who knows where they are? We've got our subject who sat down at our SIGGRAPH booth and gone through the 60 image capture, and we've done this. Somehow we have to take Face Warehouse and warp it to our subject. This is the cool thing. We have all this 3D data about subjects. We just have 2D data on this, but this sort of makes the problem more tractable. We're assuming that by having enough varied subjects that we captured, we can come up with a weighted blend of the subjects that we have in Face Warehouse to produce anybody. That may be a little bit of an overstatement, but quite frankly, okay, we have 150 people now. Maybe we do 1,000 people to make this a real product. And we can have a weighted blend of all the expressions to get whatever expression this person is making. So the question is, we have this. CR is something that we download, not for commercial use, from his website. And then these guys are the things that we want to figure out. If we could figure that out, we can figure out the face, the actual 3D face of this person. With me so far? Yes, go for it.
So when an individual changes expressions, they're not really changing their identity. But you could imagine that in this database, you might think that, like, if you smile, you look like subject 42 while you're smiling, but when you frown, you look more like subject 73 when you're frowning.
Right.
Something enforces that you have to be the same mix of individuals, the same principal components, the same coefficients all the time.
Ooh. That is a good homework question. Sorry. That's a good homework question. I suspect it has something to do with the manipulations they're doing to the Face Warehouse. But
Actually, more to do with the N-mode SVD, I think, because I'm guessing that the N-mode SVD runs SVDs. When it's running SVD on the expression axis, it fixes the identity while running that SVD, is my guess. And that sort of would conform that SVD solve over the expression to happen only for one identity set.
to add, if I can restate your question.
So it's not mutually exclusive.
Well, here we go. This is a question for the author. Is this the same as that?
How does it store identities? Is it stored in sets? Is there a particular?
But sorry, it's stored all these, the identities are slices through this thing. So this is the identity of Bob. This is stored in there. So it's a big slice of matrix or mesh data. So I think this is a reasonable, the thing that popped in my mind when I saw this is, are these transitive? Can I switch those guys? I don't know the answers. We will find out.
They're exclusive.
If they are.
Yeah, that's what it is.
But, okay, so that was your.
Yeah, that was it.
All right. So, while there are still questions, the basic concept kind of makes sense, right? We're going to be looking up, we're going to be searching for these weights that produce our person. So how do we do this? First of all, we have to talk a little bit. I'm just get rid of this. We know that. Get rid of this. First, we have to back up just a moment and talk about spaces. there are 3 coordinate systems in this thing that we have to worry about. Object coordinate. Object coordinate is the blend shapes. So we're going to represent our faces with a blend shape, which is a set of a neutral blend shape, and then up to, in this paper, they use 46 different blend shapes, all based on fax posing. All right? And so they are going to produce a mesh, a face mesh, which they call A, will be, oops, I'm sorry. A face mesh for the moment, face mesh at frame or whatever frame is equal to blend shape 0 plus, and I've written this down a bazillion times, j equals 1 to 46 alpha I blend shape I. So this is their way of representing faces. And the coordinates in this system are the alphas. So if I wanted to represent a location in blend shape space or object space, I have 1 through 46 different alphas. All right. That's one coordinate system. The next coordinate system is camera coordinate systems. All right. Once we have this is a 3D representation of a face, right? We have blend shapes, we add it all up, that's cool. Any face mesh, but of course it could be anywhere in space. So the camera coordinate system is xi is the location of our thing, and that is a transformation of our located points in there. So we'll go M, which is a 3x4 matrix, times x I, comma 1, 2. What? So this is just taking a point from our blend shape, rotating it, and moving it into. Oops. Took this away. This is the point in the blend shape, and that's just a point in camera space. So this is a 3x4 matrix, and that's typically rotation and translation thrown in there. So this is a thing that's rotating and translating. Potentially, you can do a little bit more with it than that, but right now we're just going to talk about rotation and translation. So this is basically taking our blend shape, which is defined at the origin, and it's all defined by alphas, and moving it into world space or camera space. So it's sitting in front of the camera. And then, finally, there's screen coordinates. This is all computer graphics-y kind of stuff. But there's a projection matrix, Q, that does our little projection thing. And Q has a focal length, and then you also have to divide by the homogeneous coordinate. So they say that U, which is a 2D location, that's a 2D vector, is equal to this thing that's based on Q of whatever point that we throw into it. So they did a little bit of switching of things. So blend shape, each blend shape has a vertex. The vertexes are X. We put them through this matrix, and that spots it out into the world in front of our camera. And then this turns into P. We throw that through the projection transformation, and we get U, which is a 2D location on our image plane. Easy peasy. The reason I did this is because, oh my God, you have to pay attention to which coordinate system you are in this paper. Otherwise, you're going to go insane. So we have 3 coordinate systems. Object, which is blend shape weights. Camera, which is world space coordinates. And screen, which is 2D locations. All right. So now, for each image, we need to find the transformation M, which I just wrote down, and the identity weights, Wi sub d, which I had above there. So we're going to be looking for each image. Remember, we're just calibrating the system here. We need to find M sub I, which is our camera transformation. All right. And we also need to find W sub IV and W sub expression, which, when plugged into CR times 2WID times 3W expression, and then we put this in front of M, and we put this in front of that Q thing. Woo! At the very end of this, this gives us a 2D location of that a vertex, or all the vertices of our mesh into the camera space, projected onto the screen. And these are the things we need.
Actually, the MI is the rigid transform matrix, and the pi Q is the projection, the camera matrix.
Right. Did I write this right?
Uh,
I take the expressions times
just
the chord.
just the stuff that.
Oh, right. Okay. The rigid transform. Yeah. All right. Now I'm gonna erase it. Because that's wrong. Well done. I thought that was wrong. All right. Well, in fact, now that I've written this down fairly sloppily, as long as I've written it down, I can actually write this as a minimization problem, can't I? This is the energy, the sort of difference between what I've got. So if I have 75 images, is that right? Yeah. I was 75 in groups, 1 through 75. And I take this and subtract it from U sub I sub K, super K.
But isn't the M changing for each of those images?
Yes. Thank you very much. There's some subscripts that I missed. And also, thank you. That's a very good point. There are eyes. There are also eyes there. And that would be, what? We'll get to that. That's actually important. So I is the image that we're on. And K is the, and here we go. They have a little subscript here. We got D sub K. Right. So think about what they're doing. They're saying, okay, for the one vertex, so K is, make sure I got this right, the kth landmark in image I. So this is the landmarks that we have marked out on this thing. Remember, we have all the labels and landmark. And what we want to do is basically figure out where that landmark that exists in our 3D space gets transformed into world space and then gets projected onto the screen. How far away is it from what was actually manually edited? And we're going to do this for all 75 images.
Is there anything that's common across the images of the camera intrinsic?
They assume a super simple camera. They're going to assume a pinhole camera with a fixed focal length, well, natural fixed focal length. But we'll talk a little bit about the camera stuff.
But then what do you get from doing it over all 75 at the same time? Like, is that the only thing that's shared across the things, or is there maybe the identity bit is?
Exactly. The identity bit is definitely there. So we're going to do this on a per camera basis, and then we're going to do it again to sort of lock down the identity. But at the end of it, you're absolutely right. These the MIs, they don't change on a per landmark thing. So this MI is going to be shared by a whole bunch of different these landmarks that we've got. But it is going to change on a per image basis. Because the person could be moving their head, right? They can be, while they're doing these expressions, it's really hard to hold your head exactly steady. But very good point. Given the projection matrix of the camera, we can apply coordinate descent to solve for MI, WID, and WEXP sub I. So we're going to go through and do this thing called coordinate descent. To solve for these bad boys. Okay. So much. Oh my God, we're almost out. This is a 3-paper talk just to talk about all this detail. All right, and the second step. So this is step 1 in doing all this. remember, we're just trying to figure out where the freaking points are in 3D space. In the second step, we refine the identity weights, which should be the same for all the images. So this thing is initially done on a per image basis, and we just basically say, screw it. Well, figure out something that gets close. But we're going to do this iteratively. We're going to go through and do all those things, figure out whatever identity that gets you close. And then we're going to say, you know what? The identities really should be the same across all these things. So let's lock those suckers down. This is done by fixing the transformation matrix MI. So this gets fixed. And the expression weights, expression, that were computed for each image that we set. So we're going to say, whatever values we computed for these, they're correct. We're going to assume they're correct. And we're just going to solve for a single value of WID for all frames. So they do a E joint. Oh, I'm not going to write this whole thing down, but I'll just show you that they go from I equals 1 to N. K, sorry. It's a horrible thing. Small little font. That is not a I, that is a K. That makes much more sense because this is on a per image basis. We're going to solve this thing for each one of the landmarks here on a per image basis. That was what was confusing me. It was 60 images, 75 different landmarks. All right. In the second step, we refine all these things. And so we're going to sum over not only all the images, but also all the landmarks. And we're going to do exactly the same thing. We're basically going to do a ditto of this with the this thing removed. So there's just one weight that you're solving for the entire thing. So that is almost exactly the same as that, with that one little index removed. Okay. These two steps are iteratively repeated until the fitting results converge. Convergence in their experiments is reached in just 3 iterations, which is not that bad. All right. And again, this is not the end of this. We're going to get into some of the details of this, and the paper does that as well. But the cool thing is, once we have this,
so it's a single identity. Wait, it's not like a vector of identity.
oh no, this is the yeah. So those are all vectors because remember you've got the box here, and we need an identity weight. We could have a whole bunch of values along each one of these axes, one for expression and one for identity. And it'll be a blend of all these guys, but absolutely. So at the end of it all, this is cool. We have our shape warehouse core tensor. This is basically the representation of all our faces. Times 2 WID. Think about what that does. Here's our identity axis. And this is basically saying, you sort of blend between the identities to give me a way of combining this direction. And that does not have an ID. Now, this is super extra cool. Oops. U expression. Took me a while to figure what this out is, but what are they doing here? What's this that U expression kind of thing? Just going to become clear when I do this. Oh, well, no, maybe not completely clear. What? Well, here's a hint, even more, a little clearer. DI is a big vector with the ith index equal to 1 and everybody else equal to 0. And this, remember that SVD thing? That is the U. Again, the SVD for a multimodal kind of thing is S and then a whole bunch of U's. This is the singular value vectors for this dimension. And so what this is doing is selecting out the blend shapes for this blend of identities, right? So if we knew that this actually was Bob, we could figure out the blends of, or the identity, or the blend shapes for Bob by just going through and picking out the individual expressions for Bob, right? Each one of these guys is a fax expression because that's how the face warehouse has been created. But this is not that. This is actually a blend of a whole bunch of identities. Each one's got their own weight based on that. And what we're going to be doing is saying, all right, given that, I need to get the expression that represents one of these directions, right? If I wanted the angry expression, it's actually a bunch of combos of these guys. How do you do that? Well, first of all, you lock down the identity. You basically say, okay, how do I blend these slices together? And then you take your SVD and you say, I want to choose just that one slice from here. And because it has to be that, I'm writing it like this because this is the original face warehouse. This is actually the core tensor, and so you have to use this SVD thing to do this. And that grabs that blend shape from that slice and creates it for this. So that is a blend shape where if I'm not in the warehouse, it's comboed Bob and Mary and Tom and squished them together and given me angry Doug. How cool is that?
Actually, Doug, after our discussion this morning, what I believe is happening is when the core tensor was made by running the SVD, we got this U and S being the singular values, the eigenvalues.
Right,
and
right.
then we chose the ones that were high and just threw off the smaller values.
Right.
So to then make up that core tensor's expression axis, we truncated some part of that U so that we could throw out the small singular values and not care about it.
So far.
Now, what we are doing here is multiplying the core tensor back with the truncated part of that U so that we reconstruct all of the expression axis back again.
Right.
And then still run with the PCA basis that we got for the identity weights. But then if we reconstruct the entire expression axis and just negate the SVD effect, then multiplying it back with the core tensor would allow us to get back all the expressions.
All the expressions that came in. I think
So that
you and I are on the
UXP
same
is,
page. I just went over it way faster than you did. That you much better explanation.
So the UXP thing is the truncated part of that U that we threw out when we made that core tensor.
Right. But upshot of this, whether behind the math or whatever, is basically you're pulling out a blend shape from this thing that doesn't have the blend shape in it, right? This is a person that did not sit down for face warehouse. We're figuring out the identity that makes it, kind of look like that, and then we're this kind of weird ass thing there where the D is not all that weird, but it's that little dude right there. And it's basically saying, all right, I'm going to grab the blend shape that's on this slice going that direction and pop it out there, and that's the blend shape for this thing. And then think about what we've just done. We have images and landmarks, which were done kind of semi-automatically, but all of a sudden we got a 3D blend shape rig, the fax poses for the person who's sitting in front of the camera. That's cool. That is cool, actually.
Does that not seem surprising to anybody else that from 150 faces,
You can build any face.
any face without looking at specific regions, but only the faces as a whole, irrespective of scale, or I mean,
Seems
that-
very surprising.
it seems somewhat inconceivable, right?
Now, the one thing is if you look at the results, he's getting, this thing has been correct, and Rashab and I were talking about this earlier. This has been created with connects. And you can tell that the data that's gone in here has been smooth, it's been all sorts of stuff. But, and the fact that this was connect-based blend shapes kind of makes it all the way through the process. You can see the results kind of look like they're connect-based. There's no reason. We have better technology than connects. You can build this face warehouse with more people and better meshes to capture more detail. And in fact, I think you definitely need more people if you add more detail. You want to make sure that this thing stays, robust. But that's totally possible, right?
So you're looking based on the region instead of the whole head as an entity or the whole face, right?
Yeah, but that's part of the SVD aspect of it all. I mean, there is the assumption that this is a facts-based rig, but you're
still creating the face as a linear set of blend shapes and other faces, right?
True.
So to get an exact
yeah,
shape,
you're not going to get those
exact
subtle things.
nose or exact.
But it can extrapolate past. Like it could make a bigger nose than exists in the face database.
True. Yeah, but
But blending in a face that has a bigger nose and whatever else comes along.
No,
with
because
the
I think it
face.
can blend past, right? It doesn't have to. It's not like the.
If that person with a bigger nose has a bigger face, larger jowls, that's going to come in for the wide as well, right?
well,
And there's some.
the one thing that has happened is this Chalk Talk has got you thinking. So I want you guys all to continue to think till next week, where we will continue back on this. I will know this a little bit better. And hell, if anybody knows Cal, I know he's in LA. Invite him over here and get this damn thing himself. Thank you guys. We will be back next week.
Yeah, I don't know.